Okay, so rational functions. Did we introduce what rational functions were on Friday with your class? I don't remember if we did. So remember, a rational function.
We introduced them. Like we got
Like just slightly.
We
Okay.
did.
yeah.
So f of x is p of x over q of x, where p and q are polynomials.
Mm-hmm.
Yeah.
Yeah, we did one example with this. Yeah.
Cool. But we haven't done any graphing, right? And that's going to be the big thing, is graphing these, figuring out all the information we want from these guys.
Yeah, we did the 1 through 4, how to graph like end behavior, x, y intercepts, root behavior.
I don't think that was related to polynomials, though.
Yeah, so we have that 1 to 4 steps for polynomials. We're going to modify those steps now and do the same thing for how to graph rational functions. Pretty much the same procedure, except we've got some extra caveats in here. We've got to look at asymptotes, which are going to come up, and then determining behavior on asymptotes can be another tricky thing. So let's write out our steps. So graphing a rational function. Our step 1, I'm going to recommend doing the x and y intercepts first. And x-intercepts we find by setting the numerator equal to 0. So in other words, p of x equals 0. Y-intercepts, plug in 0 for x. Y-intercepts always plug in 0 for x, no matter what function we have. That much we've pretty much done, right? If I have a polynomial and I set it equal to 0, we find the zeros. Y-intercepts, we plug in 0. What we have to mind now is that with rational functions, we have both a numerator and a denominator. So the numerator, when the numerator is 0, it's going to be 0 divided by whatever, still give me 0, as long as there's no extra zeros in the denominator. When the denominator is 0, we get vertical asymptotes. Vertical asymptotes, so I abbreviate VA. And this is just, we take this denominator and set it equal to 0. Third part, so those two parts, essentially nothing really new. Since they're both polynomials, the numerator and denominator, setting them equal to 0 and all the factoring techniques we know still apply. We just get that, we use that information to plot different things on the graph. In this case, we're plotting points. In this case, we're actually drawing the asymptotes. The third step, I recommend doing the horizontal asymptotes. This is the end behavior. Let's write out the rule for determining horizontal asymptotes in pre-calc. And then we'll do examples. We'll do one example of each, and I think that'll take our whole time of this class. So horizontal asymptotes, we've got, the biggest step is to compare the degree of the numerator with the degree of the denominator. And then we've got 3 cases. either the degree of the numerator is bigger, I'm actually kind of listing these out of order. This is the hardest case. In this case, we will get a slant asymptote. And have to do polynomial long division. That's the hardest case. We'll do that one last, and we'll warm up with some of these easier cases. If the degrees are equal, so the degree of the polynomial in the numerator is equal to the degree of the denominator, we want to compare the lead coefficients. And the horizontal asymptote is equal to that ratio. And then the easiest case is if the degree of the denominator is bigger than the numerator. Then, if the denominator has a higher degree, y equals 0. So the x-intercept, or the x-axis, is our horizontal asymptote.
Can you show the whole page for a sec?
Yeah. Those are the main parts, the first 3 steps. That's the key information. 4 and 5, steps 4 and 5. 4 is sometimes needed, sometimes not. And I'll go ahead and explain that. So step 4, what we're going to do is determine behavior around the asymptotes. Step 5 is graph. 4 and 5 we kind of do simultaneously for different sections of the graph. We'll determine the behavior for one section and then graph that section. And we'll move on to a different section. And I'll show you what I mean by that with some examples. Everyone got it? Okay, so keep those handy. I'm going to flip back to it as we're doing some examples. Let's do f of x is equal to, let's say x over 2x squared minus 2x minus 4. And all these problem statement just says to graph the following rational function. I wanted to give you guys all these steps. Step 4 and 5, so for quizzes at least, in midterms, or quizzes and big quizzes, you'll have to match at best, right? We can't graph an online thing. So at least steps 1 through 3, you want to get good at. So because determining the asymptotes, horizontal and vertical, as well as the intercepts, you pick out that key information from the graph, and then you can match your graphs, which graph matches the function on a multiple choice test. But let's go through it, because you'll probably have to do some of these on written homework at least. And what are the key features of graphing it correctly? What would Ali, what's our TA going to be looking for when you have to grade and turn in your, or when he's going to grade the assignments you turn in by hand? So let's get our graph going. So step 1 is the x and y intercepts. This one's not too bad. What happens if I take the numerator and set it equal to 0? We just get x is equal to 0. And of course, likewise, if I had plugged in 0 for x, we get 0. So our x and y intercept are the same point. We pass through the origin. Step 2 is our vertical asymptotes. And the vertical asymptotes come from setting the denominator equal to 0. We've got a quadratic equation, so we're going to have to do either the quadratic formula, or we can look to factor this guy. So if we multiply 2 times 4, we have a negative 8. And so we're looking for factors of 8. The difference is 2. And so we get negative 4 times 2. And so what we're going to do, factor by grouping, so 2x squared, we could write minus 4x plus 2x minus 4. We group first 2 terms, last 2 terms. We factor out a 2x, we get x minus 2. We factor out a 2 and get x minus 2. And so we get 2x plus 2 times x minus 2 equals 0. Let's check that real quick. Is that right? So yeah, let's use 4. We get a 2x and a minus 4x. Yep. Okay, so we've got that. We're going to set each one equal to 0. 2x plus 2 equals 0. And x minus 2 equals 0. And so we will get x is equal to negative 1, and x is equal to positive 2. These were the denominator. These are the zeros of the denominator. And since we cannot divide by 0, that's what creates these vertical asymptotes. These vertical asymptotes are a no-go zone. The function cannot cross, never cross a vertical asymptote. So there's one at negative 1 and one at 2. And then step 3, and this one, pretty easy. The degree of the denominator is bigger than the degree of the numerator. And when that occurs, it's always 0. So it's always just the x-axis. And so now you can see we've got 3 different sections, or 3 or 6, however you want to count it. Vertical asymptotes are always hard divisions. We can never cross a vertical asymptote. So that we kind of want to analyze these 3 regions. Vertical asymptotes, or excuse me, horizontal asymptotes can be crossed. The graph could cross it coming up vertically. But it only crosses inside, or somewhere in the middle of the graph. Towards the end, it will always approach that asymptote. Likewise with our vertical asymptotes, as we approach a vertical asymptote, I'm going to trace toward it, going either off to positive infinity or negative infinity. So this is going to be our step 4. And we're not given a whole lot of information about this graph. Sometimes, depending on what values we get for our intercepts, we can make an educated guess as to how the shape of the function will look, how it will behave towards those asymptotes. Unfortunately, we only have 1 point to work with. And so what's going on over here? We don't know. What's going on over here? We really don't even in the middle, we're not quite sure what's going on with that. One thing we can say is at least root multiplicity still holds. So since it's a positive x, it's a degree 1 factor. So the multiplicity is 1. So we know we're going to cross. But the question is, does it cross this way or does it cross this way? So let's pick out some more information from the graph. We do that by picking points. Near the vertical asymptotes. Let's go ahead and start over here on the left. Vertical asymptote is at -1. Let's pick a nice value at -2. And we just have to compute what the value of that is. So f of -2 gives me -2. And actually what I would recommend doing, if you can factor your function, factor it when possible. This was our denominator, right? Let's go ahead and keep our denominator factored and rewrite our function here. Let's rewrite it next to the top. And we can even factor out this factor of 2. So we can write it as 2 times x plus 1 times x minus 2. So it's a completely factored denominator. And now what's going to happen, I picked an x value of -2, and we're plugging it into each of those factors. So we will have a 2 times -2 plus 1, -2 minus 2 in those 3 factors. Numerator is a negative number. So sometimes this is easy, sometimes it's hard when you're guessing and picking these points. You can run into a lot of just computation, and there's certain shortcuts we can do. When the horizontal asymptote is 0, what are we looking for? We're looking for whether the graph in this region is either up here or down here. The graph is either going to come up and trace up to infinity, or it's going to trace downward to infinity. And then on the left, I'm either slightly above or slightly below the horizontal asymptote. And I'm going to trace it off as we move to the left. How do I know we don't cross this horizontal asymptote? Sometimes we can. Sometimes you could cross a horizontal asymptote here and then go down to negative infinity. But we know that's not going to happen. Why do we know it's not going to happen? Because we only found one x-intercept. The only way we can cross the x-axis is at points where the numerator is 0, and there's only one of those. So that tells me in this piece over here on the left, I'm either above these asymptotes and tracing it out this way, or I'm below the horizontal asymptote and tracing downward to negative infinity at the vertical asymptote. So we're either positive or we're negative. And how we can determine that, if you want, we could go ahead and compute those numbers. The other thing you can do, and things that will be useful in terms of doing rational comparisons, is doing these what are called number line tests in some sense. You are determining whether the expression is positive or negative. So that +2 is always going to be positive. -2 plus 1 gives me a negative. -2 minus 2 gives me another negative. Overall, we have 3 negatives. So this is going to be overall negative. And so even without actually computing the value, I know that the graph is negative. Will be down here. Then, what do we want to do? So our next part is -1 to 2. So this middle part here. We have 1 point, and by the multiplicity of the root, we know we're going to cross. We just don't know whether I'm crossing above or below. And so we can pick another point. Let's say we pick x equals 1 to figure out what's going on. We say f of 1, and when I plug that in, we will get 1 over 2 times 1 plus 1 and 1 minus 2. Plugging it into each of the factors, we have a positive in the numerator, that 2 is positive, 1 plus 1 is positive, but 1 minus 2 is negative. So, overall negative. Which means we're actually going to be crossing this way. So at 1 was the point I plugged in. I know I'm negative. So we are going to be going something like this. Crossing at that root. And then curve down and look like that. The other thing you can think about is the multiplicity of the vertical asymptotes. So the vertical asymptotes, this vertical asymptote came from this factor of x plus 1 in the denominator. It's a degree 1 multiplicity. What does that mean? It means we are crossing infinity. So in some sense, that means I'm going down to negative infinity, and then we are crossing and coming out the other side. So we could have determined that since this end's going to negative infinity, this side has to come from positive infinity. And then since we're crossing the graph, we could determine the behavior over here. If this were like an x plus 1 quantity squared, when that occurs, I have both ends pointing in the same direction, both sides either going to positive or negative infinity. Our last section, well, so we can reason similarly. We are going down to negative infinity on this end, but it is a multiplicity 1 factor, which means I should come out this positive one. We are crossing to the other side of infinity, and we're tracing out the asymptote like this. If we want to check that, so in this step 4, we could go ahead and pick another point. Let's say pick f of 3. 3 plus 1, 3 minus 2. All the numbers here are going to be positive. Positive divided by positive numbers. Everything's going to be positive, so it should look something like that. Any questions on that? All right, let's take a look at the other ones. I lost my list. I suppose we've got f of x is 2x minus 4 over x plus 2. This one's a bit easier. We've got just degree 1 polynomials. So let's find our y-intercepts and x-intercepts first. So y-intercept is going to be minus 4 over 2, so negative 2. And our x-intercept is just 2. Our vertical asymptotes, we set the denominator equal to 0, negative 2. And then now we want to determine the horizontal asymptote. So the degree of the numerator is equal to the degree of the denominator. So what we want to do is compare the coefficients. The horizontal asymptote is then going to be y is equal to the ratio of those. So the coefficient in the numerator, leading coefficient is 2, leading coefficient in the denominator is 1. So y equals 2 is our asymptote. So step 4, we want to determine our root or the asymptote behavior, step 4 and 5, and then graph that. Over in this region, we essentially know what's going on by those 2 points. You can kind of see I have to trace the graph, something like this. Since we're tracing this, we're tracing out to that horizontal asymptote at infinity, tracing down to negative infinity, or down, yeah, to negative infinity with this vertical asymptote, we essentially have to have this shape. Otherwise, I would have to hit this point and then cross the x-axis again, which we don't have any other x-intercepts. And if my graph were up here, I would never touch those points. So that's going to be the shape on that right side. So that one's good. We got that information from the intercepts, which we had already found. Now we got to determine what's going on this side. Are we up here or are we below? So go ahead and let's pick a point. And let's check x equals 3. Where is the graph at that? In this case, unfortunately, I would recommend computing things out. And why is that? In the last case, I only needed to determine positive or negative because our horizontal asymptote was 0. All we had to figure out was, is the graph above or below 0? Is it positive or is the graph negative in each of these regions? Here, we actually need to determine, are we bigger or less than 2? Because 2 is my horizontal asymptote. So we kind of got to get a numerical estimate to do this. So we will have 6 minus 4 gives me a 2, and then the denominator gives me 5. Is that right? Did I do that right? So we plug that in. Frequency of 6 minus 4 gives me 2. Denominator gives me 5. 2/5 is actually pretty small. It's going to be like right there.
Would we not be using -3 instead?
That's what I did wrong. I'm like, no, this is working. Ugh. Forgetting these minus signs. Thank you. X equals -3. To +3, we were at 2/3. That's kind of the point we found over here. That's why I was computing it wrong. Always missing those minus signs. So things to look out for on quizzes too. We kind of anticipate minus sign errors. Sometimes put false answers, so always double check that. So thank you for catching that for me. Let's go ahead and put -3 in there, -4, and then -3 minus +2. And so we get -10 over -1, and we get 10. So ignore that point. At -3, our function is 10. So that's kind of way off the charts, but at least I know we're like way up here. And so what's the graph going to do? We at least know that we are going to be in this quadrant above y equals 2. Any questions on that guy?
Yeah, can you kind of show us when you were doing the x-intercepts again and like where you put them on the graph?
Yeah, so the x-intercepts is here.
Uh-huh.
This is our x-intercept. This is our y-intercept. X-intercept, you take the numerator, set it equal to 0. To solve for that, we add 4, divide by 2, we get x equals 2.
So then what was step 2?
Step 2 is the asymptotes.
Oh, okay.
This guy is equal to -2. That's our denominator equal to 0.
Got it. Thanks.
Yeah. Okay, so let's do one more example, and these are the hard examples. What happens when the degree of the numerator is bigger than the degree of the denominator? Let's do f of x is equal to x squared minus 4 over x plus 1. So, yeah, let's find our x and y intercept. Y-intercept, -4. Our x-intercepts, set the numerator equal to 0. And so we will get plus and minus 2. So those are our intercepts and our y-intercepts down here. Our vertical asymptote is -1. And now we got to determine the slant asymptote. And so since the degree of the numerator is bigger than the degree of the denominator, we need to do polynomial long division. So we are dividing x plus 1 into x squared minus 4. Since there's no linear term, I'm going to go ahead and put the plus 0x as a placeholder for my x squared minus 4. We compare the highest coefficients. X goes into x squared, x many times. That'll give me an x squared plus x. Subtract off all of that. 0x minus x gives me a negative x. Bring down the -4. X goes into minus x, -1 times. We multiply -1 by that factor, and then we subtract that off. X's will cancel, and then I'll have a +1 and a -4. So our remainder is -3. What this tells us is that our original polynomial could have been written like this. We've got our polynomial part plus the remainder over the denominator. Now, what's going to happen as x goes to infinity? When x goes to infinity, well, if we just look at this rational part, the degree of the numerator is always 1 less or more than the denominator. In other words, we kind of just talked about what's happening with these guys. What's the end behavior of just this part? As x goes to infinity or goes to negative infinity, this gets really, really small. X gets really, really big, but the numerator isn't changing. So it's like -3 divided by a really big number. So that's going to go to 0. That's where that horizontal asymptote of 0 essentially comes from. And so as x gets really big, as x goes to infinity, this number is going to get really small, and it's going to look like this function. Essentially, this polynomial part dominates. It's going to look, the function is going to look like that as x gets really big. And so what we're going to do is just graph this part. This is what we call our slant asymptote. So we want to graph x minus 1. And how do we graph a line? Well, the intercept is -1, and then we have a slope of 1. So we're going to go up 1, down 1. And so we graph that line, but graph it as an asymptote. Make it a dotted line. And now we have to do our step 4 and 5. So on this side, we essentially already know how we're going to behave near the asymptote. You can see by those points which side we're in. We are definitely going to be below in this quadrant, which means function's going to look something like this. It's kind of like the last example we did, except now instead of that horizontal asymptote, that horizontal asymptote is slanted. So we get kind of like a wide hyperbola. Likewise, on the left of the vertical asymptote, what do we have to determine? We have to determine, are we above or below the slant asymptote? And we already have 1 point over here. So just based off of that point, we can determine that we are up in this quadrant. And when I'm saying quadrants in this case, you kind of have to forgive me, I'm talking about the quadrants relative to these asymptotes. So either in those 4 regions. On either side of a vertical asymptote, I have to be in one of these. Sometimes we can cross, but most often we don't. The other things we could have determined about this asymptote, it is a degree 1 asymptote, or a multiplicity 1 asymptote, x plus 1. So it's a factor with a multiplicity of 1, which means that near that asymptote, one piece is going off to infinity, the other one's going off to negative infinity. So because we determined this one's going down to negative infinity, this one has to be coming up to positive infinity. Any questions on that guy?
So for like, I know we use the x minus 1 as a slant asymptote, but like what happens if once we divide, it's still like a quadratic or something, like it's a parabola or something like that?
Then you get a parabolic asymptote.
That's crazy.
Yeah, it can happen. And I think there might be some of those on WebAssign. So this one was nice. They're all called slant asymptotes, but it's really whatever that polynomial part is. If you get a degree 2 polynomial part, plot that exact polynomial with dots, and that is the asymptote. You can get parabolic looking asymptotes. It's really weird. Okay, so looks like we got about 5 or 6 minutes. Let's do one example. I'm not sure how in depth we need to cover rational inequalities. And that is something I want to go over. I'm not sure how well we're going to test over it, but it is something that is really important for calculus. So let me find an example here. Let's do something like solve. Let's do 2x minus 6 over x plus 1 is greater than or equal to 0. So we didn't quite get to talk about this with polynomials either in doing polynomial inequalities, but the same methods apply. We want to draw a number line. Plot the zeros of the numerator and the denominator. And then 3, we're checking values. This is actually very similar to what we just did in the graph. In some sense, what do we have? We have a rational function, and when I'm asking, where is this rational function bigger than 0? It'd be like looking at our rational function and asking, where is this rational function above the x-axis? So if we had this inequality greater than or equal to 0, we would be able to find where the function is bigger than above the x-axis. So from purely analytical standpoint, some of the work, it's actually going to look very similar. We're just working with a number line though. And this is going to be the values of the function, and we're just determining whether they're positive or negative. We're looking for the x-intercepts and the vertical asymptotes. Because what can happen, so let's pull up some of these other examples. As we just saw, here's a graph, and I said, well, where is this function positive? Well, we determine it's positive because we figure out where it crosses the x-axis, and then we figure out which side of that 0 is it positive. On the right side, hey, look, I'm positive. On the left side of the 0, hey, look, we're negative. Now, the problem with rational functions is we do this magical thing where sometimes I'm negative, I'm really negative, I'm even more negative. We're so negative that on the other side of the asymptote, we become positive. We can go all the way down to negative infinity and come out the other side, and all of a sudden we're positive. So we have to keep track of these vertical asymptotes, which is what we're doing in the second step. So our zeros, 2x minus 6 is equal to 0. So add 6, divide by 2, we get x equals 3. So we'll put a mark and put a 3 on our number line. The zeros of the denominator, and always be careful with this guy. X plus 1 is equal to 0. We get x equals negative 1. But since this was a denominator, what I'm going to do is actually at negative 1, I'm going to put an open circle. And at 3, if you want, you can put a closed circle. I know I'm equal to 0 here. I cannot be equal to 0 there because it's an asymptote. And now what we're going to do is just check values. This is kind of similar to what we were doing in step 4. And what do we need to determine? We just need to determine, is the function positive? Is it bigger than 0 or is it less than 0? So if we have f of x is equal to 2x minus 6 over x plus 1, you want to factor it. This one doesn't need to be factored since most of the numerator and denominator are fairly simple. We could factor the numerator and pull out that factor of 2 if you want to make your life a little easier. But now what we're going to do is we're going to check values in each of these 3 regions. So let's just pick x equals negative 2. And when we do that, we get negative 2 minus 3 over minus 2 plus 1. But again, this is one of those situations, since we're comparing with 0, we don't actually have to compute this. And it often comes up a lot in calculus and some pre-calc problems where the numbers you have to pick, sometimes it's hard to actually compute that out and can waste some time. So the other thing you can do is write it, well, negative 2 minus 3, that's a negative number. The numerator overall is negative. the denominator minus 2 plus 1, overall it's going to be negative. A negative number divided by a negative number, overall is positive. So what I do, I come up to the number line and put a plus there. I know that the graph is positive in that region. We pick in between. Let's go ahead and pick 0. Pick a nice number in between minus 1 and 3. What's that going to give us? Negative 6 over 1. So I just plugged in 0. So the original function is negative. And then in our last region, let's pick a number bigger than 3. Let's say 4. So that's going to be 2 times 4 minus 3 over 4 plus 1. And that's just going to be a positive divided by a positive number. Overall positive. And so we get a positive. Once you finish with the number line, I would say go back and answer the question. So go back to the original inequality. What are we looking for? Because it actually didn't quite matter what that sign was, greater than or less than. We had to go through each region to figure out which one was. And now we can go back at the very end. Which ones do we want? We want bigger than 0. So we want the pluses, we want the positives. And we want any dots where it's equal to 0, since we have an equals to 0. And this is why it's important. You can't keep that asymptote. Even though that's where the denominator is equal to 0, it's where the function is undefined. So we can never include negative 1. So we want all the pluses plus all the dots with a greater than or equal to. And so what is our answer? We want negative infinity up to negative 1, but we are not including negative 1. The middle region is negative, so we're not going to include that. And then we want 3 up to infinity, but I can include 3 on that end. So go ahead, I would actually try to recommend graphing this on your own. And what you should find if you're following all the graphing steps and did it appropriately, you should find that on this asymptote from negative infinity up to negative 1, we should have a positive, the function should be above the y-axis, above the x-axis. And then again, from 3 to infinity, the function will be above the x-axis. Any questions?
Do you know what's even better? You even tested in the lecture that we're doing today.
I'm sorry, is that a question or is someone else just talking in the background? Okay, so no questions. So thanks for a good class. Unfortunately, we did not get to the IC. Try to check that out on your own because we are jumping straight into exponential functions on Wednesday. So go ahead and stick around if you have any questions. Otherwise, I'll see you then.